Hello everyone, welcome back to this channel. James here. Today we're going to look into system software of A-level computer science. But personally, I think this chapter could be renamed into operating system because that's what we will be looking at. And that's the chapter outline. We'll first look into an introduction to operating system and then talk about how the operating system handle input and output, scheduling, memory management, and what are the facilities provided to us user. And lastly, we'll end it with a very interesting topic called translation software, which is a software that converts programming codes into binary that computer can understand. Now, let's move on. Let's look into first how the OS is launched when you first start off the computer. So you're going to switch on, and what happens is that BIOS, basic input-output system, in the ROM, read-only memory, will start a bootstrap program. And this bootstrap program will load the OS into memory and sets it running. So in other words, OS is actually not the first thing that runs, right? It is launched by the BIOS. And for operating system, there are actually two modes that we didn't cover in the previous chapter. First mode is the user mode, which is what you are currently experiencing on your phone, on your computer. They are available for us, and it restricts application direct access to system resources. Whereas on kernel mode, think of it like a very transparent mode where everything can be run, unrestricted control, and access to hardware resources. So this is the logical structure of an OS. We're going to look into how they actually work. So for this structure to work properly, each higher level needs to be fully serviced by a lower level. So there's a typo here, not highest, higher, and which is hard to achieve in practice. So what it means is that hardware interface is going to support the kernel, which will run all the time, unrestricted access. And the kernel of the OS will run the utility software, and this utility software will run some of the application program, which will provide to us, the user, the interface. And the other structure of an OS looks like this, whereas the kernel will invoke specific service, as needed, and might resemble a microkernel configuration, where the kernel's functions are minimized to their essential components. So this is the modular structure. But we're not going to dive deep because that's not the main point for our lecture. The main point is what an OS does internally to make sure that your computer runs properly. So we're going to look into the internal viewpoint and the external viewpoint. And this is something that we don't see, but the OS is consistently be doing. In the next subtopic, we're going to talk into how OS handle I/O and how they manage CPU processes. 20.3, 20.4, we're going to look into memory, and 20.5, we're going to look into what facilities OS provide to the user. Now, let's look into the I/O, input-output system. So do note that this input-output doesn't just refer to the input that user give it to the computer. It also involves the data transfer between the various software. For example, the driver to the memory, to the CPU, and also data transfer between memory and CPU. So all this data transfer needs to be managed by something, and that something is the operating system. So we have a diagram here that illustrates how different software might need to talk to the components in our computer, CPU and the memory. So this, I put in a transfer rate that shows you how input-output can happen between the various components. And as you can see, screen is the fastest, and followed by this and keyboard. So that's how they handle I/O, whereas the other stuff we're going to look into is CPU. Look, we learned in the previous video is that CPU can handle processes, but then to achieve multitasking, meaning they have many processes to handle, but then how can the OS decide which process gets the CPU first? Meaning it's a little form of resource management here. So we have a few scheduler that does the job. High-level scheduler prioritize processes for admission into the memory, meaning they decide which processes in the disk gets into the memory. And the medium-term scheduler will move the program back to memory, move the program back to disk when memory gets crowded. Whereas the low-level scheduler here, low-level doesn't mean that it's inferior, but then it just means that it does different things. It selects ready processes from the memory and put it into CPU. So there is a process going on behind the hood on how which processes get the resources first. And then, yeah, this is what OS does. As a user, I don't have to worry about not having enough CPU, because they will manage it for me. So before we look into how the CPU schedule these processes, we need to understand a few terminology. So a process, which I have mentioned a few times, is a program in memory. So look at this black color box that has an associated process control block. And this process control block is a complex data structure, which I created a diagram here just to help you visualize, that contain all data relevant to running of the process. And once in memory, the state of a process can change from running to waiting. Now let's look into what are the process state. So when a new process arrives in memory, scheduled by the scheduler, a process control block, PCB, is created, is in ready mode. And then when the process is given access to the CPU, meaning it can now use the CPU, it would go to the running state. And when the process is halted, it will get back to the ready state again by an interrupt, meaning if it hasn't been completed yet, the process. And then what happens if the process cannot progress until some event has happened, meaning it's halfway there? That's when OS put the process into waiting state, and then process is notified when an event has completed. It will then put it back to the ready state. And if, let's say, the process has completed running, the process will be terminated. So that's how process can be in different states. Let's look into what also thread is. Thread is a part of a program which is handled as an individual process when being executed. So let's say you're running an individual task. So like video editing. That's when there are many processes running behind the hood. So a thread is just one of these processes. Or sometimes interrupts can happen. So there are a few reasons. Because processes consist of alternating period of CPU usage and I/O usage, there are times when I/O takes just too long for CPU to wait for it. And this is why interrupt mechanism is used when a process in the running state makes a system call requiring an I/O operation, so that it's effective. The second reason why interrupt can happen, we will look into how it works later, which is when scheduling algorithm decide to halt a process based on the priority. But that one we'll discuss it. So regardless of what the reason an interrupt happened, the operating system kernel is responsible for executing an interrupt handling routine, basically a routine that handle interrupt, okay, which might involve determining the priority of the interrupt. An essential task is to save the current register value into the process control block, meaning if the program were to handle an interrupt first, it needs to save whatever the value that is inside the current register into somewhere like the process control block, so that when the interrupt is handled already, we can put the value back into our CPU. So now let's look into scheduling algorithm. How does the CPU handle how does the OS handle CPU usage? How does it manage so many processes? There are three different ways. The computer scientists categorize it into non-preemptive and preemptive. Non-preemptive scheduling lets the process run until completion. Alright, they don't stop it. Whereas preemptive, they allow operating system to interrupt a running process to execute another with higher priority, which is these two algorithms here. Now, the first one, the non-preemptive, is first come, first serve. It's pretty intuitive. Basically, if your process comes first, the user launcher first, it's going to be executed first, one after the other. So you can see from this diagram, after process 1 is executed, then process 2 will be executed, and process 5 will be waiting. First come, first serve. Whereas the first preemptive algorithm is the round-robin algorithm. So it is a CPU scheduling that allocate a fixed time slices to each process. So let's look into this example here. Imagine I'm running 3 processes, and then process 1 will run first for an allocated time slice. So at this time, even if process 1 it hasn't been fully run, it will still be moved back to the queue to let process 2 run for a while, and then process 3, and then process 1 will get its running time again. So this method actually allows multiple programs to run concurrently. So process 2 doesn't have to wait until process 1 to fully process to run. All right. So that's how round robin algorithm work. The other one is priority based scheduling algorithm. It is a CPU scheduling algorithm that assigns CPU time to processes based on their priority. So in this example, process 1 is running. So using the first come first serve model, process 2 should run next. But if process 4 has a very high priority, then in the next clock cycle, process 4 will get to run first instead of process 2. So that's priority-based scheduling algorithm. And for the CPU to determine priority, these are something they look for. Estimated time or process execution, how long does it take? Estimated remaining time for execution. Length of time already spent in the ready queue, how long has it been waiting? Whether the process is IO bound or CPU bound. So that's how a few scheduling algorithm. Hopefully that makes more sense with all the visuals. Now, we know that the OS can handle, from the internal viewpoint, it can handle IO, it can handle CPU management. Now, this is how it manages memory. So it allocates a secure memory space for the OS kernel, and then it will load a program into memory by specifying memory addresses for the program, meaning it allocates space for processes to run. And in a multi-programming environment, managing memory can become complex, meaning many tasks running at the same time, potentially leading to fragmentation. So the medium-term scheduler might relocate a process from main memory to alleviate this issue, meaning we take the process out of memory into the disk to let other processes go in. So this is to allow multi-programming to happen. And decision also need to be made by the OS regarding the allocation of memory portions for individual processors, meaning how much space should I allocate to this process. So all these things are done by the operating system. Now I want to show you an example of how the OS manage memory. There are different approaches. The first one is the segmentation approach. So a large process like the OS, music, your Google Chrome, it's divided into segments. These are segments, but the segments are not constrained to be on the same size. So this is one of the disadvantage. We'll talk about it in a while. So what happened is that the OS initially, the earlier approach is to partition the memory, so to 1, 2, 3, 4 partition, and then let the whole of a process to go into one slot. This approach has its flaw because look at these empty spaces here. If, let's say, the music doesn't take up too much memory, but then it's still allocated one partition, this will waste partition size, the memory. So what happened is that later they developed dynamic partition that allows the whole of the program to be loaded into not a fixed size partition, but a dynamic size. So we can save up memory here. But this approach is still not very good because, first of all, segments were not constrained to be the same size. And then size of the process did not allow all of segments for one process to be in memory at the same time. So what do I mean by that? Look, imagine that these are the processes that are currently running, and after a while, some of the process just finished running, and we have some empty space in our memory. What happened is that if let's say you're running a game that needs a lot of processes, they can't find a spot because these processes are contiguous. So these two factors leads to memory defragmentation. Fragmentation result in degradation of the performance. So what is the solution to this? Modern approach is to use something called paging. So first thing you need to understand is that in paging, process is divided into equal size pages. And memory is divided into frames of the same size. So hopefully now you can see what I'm going to do next. So what happened is that instead of putting everything into one slot, we can put stuff into different slots. But before that, let's understand what logical memory is. So the logical view in paging refers to the contiguous memory space presented to a process or program, abstracted from physical memory by using logical addresses. So this is just a view that the program see. But what happened under hood the physical memory is that processes are not arranged in contiguous space. But how can the OS do this? This is when things comes into play. They have something. Paging uses a page table, which is a data structure used by OS to map logical memory from a process into their corresponding physical address in memory, facilitating memory translation and management. So this is the actual way processes are stored. But what appeared to the processes and program is the logical memory. So in other words, the OS is doing something behind the hood to allow dynamic partition size. So that's a page table. Now another term in this example is virtual memory. Now imagine that physical memory is full. There are times when the controller will need more memory. That's when they use part of the hard drive to act as a memory space, so which is essentially the virtual memory management system that uses this space as an extension of RAM to temporarily store data when physical memory becomes insufficient. So another term, disk thrashing, which is also discussed in your syllabus, is a situation where computer performance drastically slows down due to excessive swapping of data between RAM and the hard disk. So what happened is that when using virtual memory, some of them, because program can't run here, so then they will need to swap very often. So at a point when everything they do is swapping, they can't do anything. That's when the condition disk thrashing comes in. So that's how, not a very detailed explanation, but hopefully it explains better how the CPU actually allocate memory to different processes. So the segmentation approach is not the best, therefore now the paging approach is used. So memory management is done. We have looked into all the internal viewpoint of how the OS handle resources. So now let's look into what facilities it will give to the user. It's just a very short subchapter. First of all, user interface, command line, graphical display, which is how I'm interacting with my computer right now, voice recognition like Siri. Second is that they also provide device driver, which allows the peripheral devices to communicate with the computer. File system, how they create folders, subfolders. How we can do that is because OS provided the facilities. Programming, they help us provide an environment for us to program. And making system code, they enables access to its services, like, for instance, when a program requests file data, the OS convert this into a system call to locate and provide access to the file for the program. So these are the facilities that OS provided for the user from an external viewpoint. Now, another thing that OS also do is sometimes to provide the translation software. And we are going to dive very, very deep into how translation software can take programming language and convert it into binary code that the user can understand. Okay? So let's look into a compiler. So we know that compiler compiled code into binary, into executable code. And then today we're going to look into the internal structure of it, which consists of the front end and also the back end. And in the front end, they're going to analyze and then create intermediate code. And then at the back end, they're going to synthesize the object code. Now, let's look into the more detailed version of the front end. We're going to go through each process one by one. So I have my source code. How do we conduct lexical analysis, syntax analysis, semantic, and eventually generate the code. Now, level 1, step 1. Let's say this is my code, and then how the compiler will read is that first it will run a lexical analysis. So it will remove all the white space and all the commands, then to take each line of source code and identify each lexeme. So what is a lexeme? It refers to the smallest unit in programming language, for example, identifier, keyword, operators, and symbols. So in this one line of code, I actually have 5 lexeme. Keyword, variable name, symbol, keyword, symbol. So that's the first step. The second step is that the analyzer will also categorize each lexeme in order to tokenize it. So tokenization is a process that segment a sequence of character into meaningful unit, meaning to identify whether what is this lexeme, what is another lexeme. In this case, the keyword, identifier, symbol, keyword, symbol. That's step 2. Step 3, the identifier here, first name, will be entered into a symbol table, which looks like this, has the identifier, what's the data type, and where it is located. Step 4, another table is created to identify the relevant token for each lexeme that is not an identifier. So like var, dart, string, etc. So now we have done lexical analysis. We have all the symbols in the table respectively. Now syntax analysis, check the arrangement of token against language rules to create a structured tree representing the code syntax. So imagine I have this line of code here. What syntax analysis it will do is that it will see whether the order is correct. By the way, this is called a structured tree. We'll look into how to derive an expression from this later. Next, semantic analysis. The next step, it checks codes for logical error and ensure it follows the language meaning and rules beyond its structure. So for example, in this case, in Python, x is an integer, y is a string. So what semantic analysis will detect is that the line tree cannot be run because you can't add a number to a string. So that's an example of semantic analysis. So we have talked about analysis, but let's pause to talk about how compiler can represent the grammar of a language. So in this example here, it basically says that when you are creating a variable, you can start off with the letter only, followed by a letter or digit. And you can't start off with digit. So that's just one example of how to define the grammar of a programming language. Another approach is to use the backwards noun form. So for example, identifier, in this case, it can be a letter. This bar stands for or, and identifier letter, identifier, or digit. And digit has to be from 0 to 9, letter, uppercase or lowercase. And then what happened here is that when it talks about letter case, instead of writing A to Z here, we can create another thing called uppercase letter. So when it refers to uppercase letter, this means that it involves all the possible letters here and lowercase letters. So you can see that this refers to this, lowercase letter refer to this. So that's backwards noun form to actually explain how the grammar of a programming language is like. Now, backend synthesis analysis. So we have looked at front end. What the backend will do is that they will produce synthesis of the object code. So if an error exists during the front end phase, it will present all the error and explain each error and state where it occurs. If an error does not exist, this backend process will generate machine code from intermediate code. They will also do code optimization. So this is when the stuff is not optimized. You can see that they declare the same thing, A and B, A times A minus B. And Y, again, they do the same thing. So what happened is that the CPU will need extra processing power. But if you were to optimize it, you can actually do just Y times 2x because that's the same thing. So this is something that the backend processors will do as well. Now, the last part is how computer can read this line of stuff here. We know that it's A plus B times C, but according to the rule of mathematics, B, the multiplication has to go first. But how does the computer know this? There has to be an algorithm that handles it. That's when we need to convert something like that. They will convert something like that into reverse Polish notation, allow for easier and more efficient evaluation of mathematical expression, and they also eliminate the need for parentheses and following a postfix notation. Let me explain what a postfix notation is. So by the what it means is that this is my structure table. A postfix notation, just remember that it will look into the left and the right first before going to the middle. For example, to evaluate this structure table, the postfix notation is B. Instead of the star here, I'm going to go to C before I go back to E. So B times C is the infix notation, but in the postfix notation, it will be BC times. Let me give you another example. So the postfix notation for this diagram, A plus BC times, will be A, do nothing, BC times, and plus. So look into the left, right, then the middle. So that's what postfix notation is. You also have prefix, infix, but that's not what we will talk about. Why do we need to learn this? That's because there are times when you need to convert a postfix notation into infix. So let's say this is the question that the exam give you. How can you convert it? Now let's look into it. X, we start off X again. Remember left hand side, 2 right hand side, then the middle. So what can we see here? It's X times 2. Okay. Y, 3, and the multiply star. So we got Y times 3. Now this entire thing here, left, right, and then this plus symbol here, we got X times 2 plus the Y times 3. Again, this is my left, 6 is my right, followed by the divide, and the expression will be X times 2 plus Y times 3 divided by 6. So this is how you convert a postfix notation, reverse Polish notation back into infix. Now there's another way to do this using a stack. In fact, you have to follow this shunting yard algorithm. It looks complicated, but trust me, it's not really hard. Now let's try to use this example. So I have my stack line here, RPN line. So what happened is that in this algorithm, you need to have an RPN line. You start off here. Either you go to the stack line or you go to the RPN line. That's the algorithm. Let's look into it one by one. Imagine that this is our expression. Tokens of expression, meaning we're going to start off with A one by one. So if it is an identifier, it passes straight through the RPN expression line. So my first character, A, is an identifier, not a symbol, not an operator. So I'm going to put A into RPN line, followed by the plus. But the plus is an operator, and there are two conditions. If the stack line is empty or contain a lower preceding operator, the operator is diverted into a stack line, which is what I want here. B is an identifier, so I'm going to put it into my RPN line. Look, this is how the algorithm works. It's either you go to RPN or you go to the stack. Not very hard. Followed by the times operator. Again, the reason why we put in the stack line is because times operator is higher than the plus operator. We'll execute this first. Now C will then be put into the RPN line. Now, when all the tokens have left the infix line, meaning there's nothing here already, the operators remaining on the stack line are popped out one by one from the stack line into the RPN line. So pop means the first one will go first. So I'm going to pop the star into my RPN line, pop the plus into my RPN line. So this is how I use the shunting yard algorithm using stack to find out what's my postfix notation. Now that's another way to do it, which sometimes you need to evaluate an expression given the value of variable. Imagine that this is the expression in postfix, and then they tell you that x equal to 5 and y equal to 3. How do you figure out the value of this expression? Now the algorithm is simple. Values are kept added into the stack until it meets an operator. So first, I'm going to add 5. My value is 5. Because x is 5, y is 3. Values are kept added into the stack. Remember, the stack means last in, first out. I'm going to add 5, 2, and then I'm going to add into my stack until it meets an operator. What does it do? Then the top 2 items in the stack will be popped out, and a new value will be created and re-added back to the stack. So now the next symbol is the times operator, which is an operator. I'm going to bring 2 and 5 out, multiply them, and the result will then be added back into the stack. Go back. Now I'm going to have value 3, 3 again, so I'm going to put 3 into my algorithm, my stack, another 3 into my stack. Now since I made an operator, I'm going to multiply it. 3 times 3 equal to 9, and then put it back to the stack. Made an operator, take them out, add it back to the stack, add 6 to the stack, made an operator, divide the 2, and then put the result back. So the expression, the value of it, will be 3.16. So that's how a simple algorithm like that can help us to evaluate an RPN expression. I believe that if you understand this, you can answer most exam questions. And that's pretty much it for today. That's system software. We delve deeper into what an OS does. And we also look into how translation software convert source code into machine code instruction set. So that's the end of this video. Thank you so much for watching. I'll see you in the next video. Goodbye.